Chapter 3 Measurements in Chemistry. On December 11, 1998, NASA launched the Mars Climate Orbiter into space. Its mission, to study the Martian climate and relay messages to a lander on the surface of Mars. All went well until September 23, 1999, when NASA officials lost contact with the spacecraft as it tried to enter the Martian atmosphere. They later learned that the Mars Climate Orbiter had penetrated the Martian atmosphere too deeply, and more than $125 million of science equipment vaporized in the Martian atmosphere. What happened? Engineers had done extensive calculations to determine the best altitude for the craft to enter Mars's orbit, about 150 kilometers. One team programmed the flight system software on the orbiter using the metric system, but another team programmed the ground-based system in the U.S. customary system. The two computers were speaking different languages. So, instead of entering orbit at 150 kilometers, the craft descended to 60 kilometers. The tremendous forces acting on the spacecraft at this altitude tore it to shreds. 3.1 Measurement Systems. 3.2 Measurements. 3.3 Problem Solving in Chemistry. Questions. What is a measurement? Why do we need standard units? What units are used by scientists? What are the benefits of the SI? How can I change units? Terms of measurement. SI, fundamental unit. Derived unit. Unit conversion. Conversion factor. Why do I need to learn the metric system? 3.1 Measurement Systems. Measuring and the creation mandate. What is the diameter of an oxygen atom? How fast does a chemical reaction occur? How much energy is released when 1 gram of hydrogen burns? The answers to these questions can be found only by measuring. In the beginning, God ordered man to subdue the earth and have dominion over the creatures living there. This charge, what we called the creation mandate in chapter 1, does not imply that humans are only to occupy the earth. Rather, we are to actively pursue knowledge about the earth and the living things that inhabit it. Gaining knowledge about God's creation so that we will be able to benefit others is a major purpose underlying the study of science from a biblical worldview. One of the key ways to gain information about creation is to take measurements of many different aspects of nature. Measurements are quantitative data about the world around us. What is measuring? You have probably measured things before. If you enjoy woodworking or carpentry, you have measured the length, width, or thickness of boards. If you cook, you have measured dry and liquid volumes of ingredients in measuring cups. But have you ever considered what measuring involves? Could you describe how to measure in your own words? A measurement is a comparison of an unknown quantity to a known standard unit. Many phenomena have measurable characteristics. For example, scientists measure quantities such as length, mass, volume, time, and electrical charge. These measurable properties are called dimensions. Before a dimension can be measured, there must be a unit of measure defined for that dimension. For example, you are probably familiar with the meter as a unit of measure for the dimension of length. Other units for length include the kilometer, mile, and inch. The word unit means one of something. Dimensional units are lined up on a scale to provide a means of measuring. The scale is graduated or accurately subdivided into measurement units. A graduated scale is essential to every instrument designed to measure anything. An instrument is an artificial device made for refining, extending, or substituting for the human senses when measuring. A measurement consists of two parts, a number and a unit. A unit is the standard by which the scientist compares the object. But what standard should we use? Metric system of measurement. With the increased emphasis on experimental science during the 17th and 18th centuries, came a desire to share research across Europe. Scientists quickly recognized a problem in that scientists were not using the same measurement units. They needed standardized units. In 1670, French astronomer Gabriel Mouton proposed a system that would become the metric system. The system was based on a decimal scale, that is, a scale that consisted of base units multiplied by powers of 10. In 1799, France became the first European nation to adopt the metric measurement system, which consisted of the kilogram and the meter. These standard units were defined by the mass of a cylinder and the length of a bar, respectively, each made of durable platinum metal. In 1960, many nations adopted the modern metric system, called the Système International d'Unités, which is French for the International System of Units. We commonly refer to it as the SI. Worldwide, scientists use the SI as the standard measuring system for their research. It is also the system used throughout most of the world for everyday measurements. The United States is one of only 3 countries that have not adopted the SI. There are 3 reasons for the widespread usage of the SI. First, it has only one unit for each measurable dimension. For instance, the meter is the unit used for the dimension of length. The units in the SI are also based on natural phenomena, and most are based on physical constants, meaning that the units can be verified easily. Finally, the SI is a decimal system, which means that units can be scaled by factors of 10 to measure larger and smaller objects. The decimal nature of the SI makes converting between units easier. SI units. There are 7 fundamental units in the SI, each of which measures a basic dimension. Scientists originally based these units on physical objects that they maintained in France. Over time, we have redefined each of these 7 units. So we now define them on the basis of physical constants, which is why they are the fundamental units. You may hear these referred to as base units, but keep in mind that the term base unit also refers to the part of the metric system that is multiplied by a power of 10 to form a prefixed unit. A summary of the fundamental units along with their symbols is shown at left. The 7 SI fundamental units. Unit, ampere, A. Dimension, electrical current, I. Basis, elementary charge, vibrational frequency of cesium-133. Unit, candela, CD. Dimension, light intensity, joule. Basis, luminous efficacy of 540 terahertz light. Planck constant, vibrational frequency of cesium-133. Unit, Kelvin, K. Dimension, temperature, T. Basis, Boltzmann. Constant, Planck constant. Vibrational frequency of cesium-133. Unit, kilogram, kilogram. Dimension, mass, m. Basis, Planck constant, speed of light, vibrational frequency of cesium-133. Unit, meter, m. Dimension, length, ELL. Basis, speed of light, vibrational frequency of cesium-133. Unit, mole, mole. Dimension, number of particles, n. Basis, Avogadro's number. Unit, second, s. Dimension, time, t. Basis, vibrational frequency of cesium-133. Some SI-derived units. Unit, square meter, m squared. Dimension, area A. Unit, cubic meter, m cubed. Dimension, volume, V. Unit, kilogram per cubic meter, kg per m cubed. Dimension, density, RHO. Unit, hertz, Hz. Dimension, frequency, F. Unit, Newton, N. Dimension, force, F. Expressed as fundamental units. Kilograms per meter per second squared. Unit, Pascal, PA. Dimension, pressure, P. Expressed as fundamental units. Kilograms per meter per second squared. Unit, joule, J. Dimension, energy, E/work, W/heat, Q. Expressed as fundamental units. Kilogram meter squared per second squared. Unit, degree Celsius. Dimension, Celsius temperature. T, C. The beauty of the SI is that we can express nearly every other unit of measurement in terms of these fundamental units. For example, we can express thermal energy in terms of kilograms, meters, and seconds. Kilogram per meter squared per second squared. But expressing a measurement in terms of several fundamental units is often cumbersome. They can become complicated and hard to remember. To avoid this problem, scientists have established other units that they have derived from combinations of the fundamental units. There are 22 derived units approved for use in the SI. For example, the unit of thermal energy mentioned above is called the joule, J. 1 joule equals kilogram meter squared per second squared. The box at left lists some of the commonly used derived SI units. SI unit prefixes. The SI allows scientists to scale units up or down so that they are convenient to measure and express quantities of different sizes. To change the size of a unit, the SI adds prefixes representing powers of 10 to the names of the base units. For example, the meter is the base unit of length, but a meter is not always the best size for a particular measurement. It is more manageable to use the centimeter, a unit that is 1/100th of a meter, to measure the length of your shoe. At the same time, to measure the distance from your house to the school, it is usually more convenient to use the kilometer, a unit that is 1,000 times as long as a meter. The prefixes used in the SI are based on foreign words for the related power of 10. As the word prefix implies, we always place prefixes in front of the base unit that they modify. Table 3-1 lists the SI prefixes with their symbols, meanings, and exponential forms. How it works: speedometer. Some of you have your driver's license by now and are familiar with a vehicle's speedometer. But do you know how it measures and displays your speed? Speedometers have been around since the early 1900s and were actually optional on early cars, but they quickly became standard equipment. Speedometers display the speed of a vehicle by measuring the rotational speed of the transmission. For many years, the usual design was a mechanical speedometer. This worked as a flexible shaft connected to the vehicle's transmission. At the end of the shaft was a permanent magnet. The rotating magnetic field of the spinning magnet would induce a current in a nearby aluminum disc. The induced current would produce another magnetic field. The interaction of the two fields would cause the aluminum disc to rotate. The disc was connected to a spring that would limit the disc's movement. The spring and magnetic forces were balanced and calibrated to the vehicle's speed. A pointer attached to the disc allowed the vehicle's indicated speed to be read from a dial. Most speedometers today are electronic. Many of these systems still measure the speed of the rotating transmission. On cars with anti-lock braking systems, ABS, the system will often use the rotation rate of the wheels, a value which needs to be known for the ABS system to operate properly. In either case, the system consists of a magnetic input device that turns the rotation rate into an electronic signal. The signal is calibrated to vehicle speeds that are then displayed on the dashboard. Speedometers have limitations just like all other measuring instruments. Some of these limitations are due to the design and construction of the system. Additional uncertainty can be introduced by aftermarket modifications to the vehicle. One common modification that can affect the accuracy of a speedometer is changing the wheel or tire size. Oversized tires travel over more ground per axle rotation, meaning that fewer axle rotations are needed to generate a given distance of vehicle travel. This produces indicated speeds on a speedometer that are lower than the vehicle's actual speed. Unit conversion. Many times we will know a measurement in a certain unit, but for some reason we need to express it in a different unit. In these cases, we use a mathematical process to change the units. This process, called a unit conversion, we multiply our measurement by a conversion factor, which is a fraction that contains both the original unit and its equivalent value in a new unit. Mathematically, conversion factors are always equal to 1. Since multiplying by 1 doesn't change a quantity, unit conversion does not change the amount of the measurement, rather just the way that we are expressing it. This process of using conversion factors is much like renaming fractions. If we are trying to add 1/2 to 1/4, we have to change the 1/2 into an equivalent fraction that has a 4 in the denominator. To do that, we multiply 1/2 by a fraction that is equal to 1, in this case, 2/2. Because 2/2 is equal to 1, multiplying by it won't change the value of 1/2. but we have now changed the form of 1/2 to 2/4. If we are trying to convert meters to millimeters, the conversion factor will contain the old and new units, m and mm. The equivalence expression is 1 meter equals 1,000 millimeters. Next, we create the conversion factor by dividing both sides of the equation by one side or the other. The two final ratios are equivalent. They are both equal to 1. But which is the correct one to use? The good news is that the problem itself will let you know. Let's look at a unit conversion between two units that you are very familiar with.